In my previous video, I introduced time as a key parameter in understanding aerodynamic lift as a logical sequence of cause and effect. This video is not a direct follow-on, but rather a separate introduction from a different perspective. The aim of this video is not to explain lift, but to lay some of the groundwork for understanding aerodynamics at molecular level. I'll be using a simulation of air molecules, which at first might seem to be random and chaotic, but they are still subjected to Newton's laws of motion in a surprisingly intuitive way. When Bernoulli published his famous work on hydrodynamics in 1738, he also expanded on the idea of gas being a bunch of particles in constant motion. In air, these particles are mostly nitrogen and oxygen molecules. The faster the average molecule speed, or more precisely, the higher the kinetic energy, the higher the collision forces. Pressure is simply the measurement of the combined forces of a lot of molecules colliding against the surface. Temperature is also directly proportional to the average kinetic energy. Let me switch to a thermal view. An individual molecule does not have a temperature, so what I have done here is to simply color each molecule according to its speed. When you hear me later referring to thermal motion or thermal speed, it is the speed of a molecule relative to the other molecules in its general vicinity. If there's one thing underlying a good understanding of molecular behavior, it's relative velocity. Any velocity is relative, which means in order to give it a useful value or direction, you need to choose some fixed point as reference. I will divide this into three categories. Closing speed is the speed between one molecule and another, or between one molecule and a solid surface. Thermal speed is a molecule's speed within a small volume of surrounding molecules, or to be more accurate, the speed of a molecule relative to the center of mass of its surrounding molecules. And thirdly, drift velocity is the velocity between a small volume of molecules and another such volume, or between a small volume of molecules and a solid object. At the lowest level, there is the relative speed between individual molecules, which I will call the closing speed, in other words, the rate at which two molecules approach each other before colliding. When a line appears between two molecules, it indicates that they are closing in on each other, and the line color indicates the closing speed. Here it is with the molecules colored according to their own speeds as well. If one molecule is traveling at 500 meters a second and the other is traveling at 300 meters a second in exactly the opposite direction, the speed at which they are closing in on each other is 800 meters per second. This is the speed that determines the force during the collision. During collisions, there is some velocity exchange going on, as you can clearly see the change in the molecule's speed color after a collision. When a collision occurs head-on, it appears as if each molecule simply reverses its original speed, but what actually happens is a direct momentum swap. It is easier to see the swap with unequal speeds. Again, it is very convenient that oxygen and nitrogen have nearly identical masses, because a momentum swap is equivalent to a simple velocity swap. If I happen to define a contained reference frame, I can once again express their speed as thermal speed. In a head-on collision, the closing velocity is constant and there is a complete velocity swap. In a glancing collision, there is still some velocity exchange, but you can see from the color of the closing velocity line that it changes speed and direction. The closing force and velocity exchange depends on the final closing speed and direction once they finally collide. If a camera could track a particular molecule, the apparent velocities through the viewfinder will look quite different, although the closing velocity is obviously the same. You could in fact choose different camera speeds, and each time the result would look different. Imagine looking at a section of a layer of stationary air. Here once again the color indicates speed. If the air is flowing, then each molecule would also have a drift velocity, and when combined, the result might look like this. Here, the color indicates the combined thermal and drift speeds. At a glance, it looks like the temperature is now higher, and you would expect higher pressure as well. But the relative speed between the molecules are still the same, therefore the collision forces have not changed either, and pressure must still be the same. Pressure and temperature within the air is therefore only determined by the thermal speeds, so it is important to distinguish between thermal and drift speed. Drift speed itself is relative because it depends entirely on how you choose your global frame of reference. If someone with a camera had to scan back and forth along this layer of air, what they will see in the viewfinder will appear to be air flowing back and forth. The drift frame of reference has no impact on the thermal speed or collision forces. So if the collision forces between molecules depend on their velocities relative to each other, what about collisions with solid objects? Again, it is only the relative speed between the molecule and the surface that determines the force. You can move the object or you can move the air. The disturbance is the same, and that disturbance is nothing other than a change in thermal velocity. A full head-on collision with an object results in the highest collision force, and the molecule gains twice the velocity of the object. A collision against a sloped surface results in lower closing speed perpendicular to the surface, and this results in a lower collision force. The shallower the slope, the smaller the collision force. In each case, though, the molecules still gain energy from the object. To a molecule, only the apparent speed as seen down a tube perpendicular to the surface is of importance. The retreating surface will have the effect of a very low closing velocity, and the molecule will actually lose energy by transferring it to the object. I will start with this very simple trapezium, which I can move as I want. At molecular level, the collisions are said to be elastic, which means they bounce off each other like hard balls with no friction or energy loss. Collisions with stationary flat surfaces simply reverses the perpendicular component of the molecule, also without friction. Now imagine that we can separate the molecules into an inner and outer layer, and for simplicity, I represent the inner layer by only 3 molecules bouncing between the surface and the outer layer. You can think of these molecules as messengers. Every time they bounce away from the trapezium with the same speed and direction, they effectively carry with them the information that there is indeed a solid body and that it is not moving. That information is transferred when they collide with the outer layer. When these molecules return from their collisions with the outer layer, they now convey the state of the outer layer back to the surface. If the trapezium starts moving, it changes the relative impact velocity between the surface and the inner layer molecules. This is what I refer to as pressure disturbance. It is the change in average impact velocity between a molecule and the surface from one collision to the next. On a larger scale, this translates to a change in surface pressure, but this change in impact also affects the molecule's velocity after the collision, which means that when they reach the outer layer, there will also be a change in collision force and affect the local pressure of the surrounding molecules. To bring it all back to airfoils, I'm going to play this simulation a number of times. On the first run, I'm examining only the collisions against the various parts of the airfoil. While it is stationary, the molecules that collide with it simply bounce away, but their thermal speed color doesn't change. As soon as it starts moving, the molecules colliding with the leading edge pick up additional speed after each collision. Slightly further back from the leading edge along the top surface, there is still some increase in thermal speed after every collision, but not as much as at the leading edge. Still further back along the rear slope, the collisions result in a drop in thermal speed. You can see the color shift towards blue after each collision. Along the bottom, there is hardly any noticeable change in thermal speed after a collision. This time I'm looking at the leading edge and including the molecules slightly further ahead. I've packed in 50% more molecules to make the result easier to observe. At first I'm going to give the airfoil a short, hard shove. Molecules colliding directly with the leading edge get shoved forward, smashing into surrounding molecules and transferring that extra speed into the surrounding molecules, who in turn pass it on further and further. The average collision force within this area of high thermal speed is high, which is why it's called a pressure wave. The individual molecules do get displaced to some degree from their general initial positions, but they do not travel with the wave. To make this wave easily observable, I had to give the airfoil an unrealistically hard shove. Compared to the average thermal speed of the molecules, the airfoil speed would have been somewhere around Mach 3. That is why this pressure wave is also a region of very high density. You won't see this high density in a pressure wave if the airfoil gains speed gradually. This time the airfoil will keep moving, but at a more sedate pace. Focus again on the region around the leading edge. As the wave from the initial impact spreads outwards, the molecules near the surface get knocked back towards the airfoil, where they again gain speed. This back and forth movement of the molecules near the surface continuously pump kinetic energy gained from the leading edge into the surrounding air. The opposite is taking place towards the rear of the airfoil. A molecule loses thermal speed when it collides with a surface. When this molecule collides with another one from further away, they exchange speed. The first molecule returns to the surface only to lose more speed to the surface. So now both molecules are left with less thermal speed than before. This process repeats, and gradually molecules from even further away end up being robbed of their thermal speed, resulting in an expanding area of low pressure. I should mention that the region of air being simulated here extends far beyond the edges of the screen, so it is not as if the air moving over the top has to squeeze through between the airfoil and the edge of the screen. Also note that this simulation only covers a fraction of a second of actual airfoil movement. It takes a whole lot longer before the overall pressure and velocity distribution resembles that of a flying wing. I will cover that process in a future video. Nevertheless, the regions of high and low thermal velocity correspond very well with the high and low pressures predicted by conventional fluid simulation. I will finish off with something that you can only really visualize with a molecular model, and that is the air property that we call viscosity. Consider two layers of air, same temperature, pressure, etc. If the separation is removed, their natural motions will cause them to start mixing, and we call this diffusion. But what if one layer had a drift velocity? Diffusion is still going to take place, but now when a red molecule wanders into the fast-flowing green layer, it is most likely going to get knocked to the right, while the green molecule that collided with it is going to lose some of its drift velocity as a result. The same happens to any green molecule drifting down into the red layer. The red layer is effectively applying a braking force to the green layer, while the green layer is applying a thrust to the red layer, trying to drag it along. Viscosity is just a way of expressing the force experienced by each layer based on the difference in their drift speed and their separation distance. Here it is with the molecules colored according to their horizontal drift velocity. If given enough time, all the drift momentum originally limited to the green layer would have been redistributed through diffusion, and all the molecules will now drift along at half the original drift speed. Any change in air property that increases the diffusion rates will likewise increase the rate at which momentum is exchanged. Here I have increased the thermal speed, and you can see just how much quicker the drift velocity gets redistributed. This diffusion interaction between layers is also what causes surrounding air to be entrained around nozzles and give rise to things like the Coanda effect. It's all very interesting, but there's not enough time for it right now. Thanks for watching.